The Heat and Frost Insulators and Allied Workers, also known as the Insulators Union, works with over 23,000 members throughout the United States and Canada. We would like to spend some time in this video to teach you a bit of the science behind insulation and the reasons our craft continues to be vital to construction. Let's begin with heat. Everything in the world is made up of molecules. Heat is produced by the movement of molecules. There are three methods that heat can use to transfer from one thing to another. The first is convection, the second is conduction, and the third is radiation. Convection is on display when you look at the heating systems in some rooms. The heated air has molecules that are moving at a high rate. Heat is the result of molecules moving. The more heat in the air, the faster the particles are moving. When those particles bounce against each other, they create more space between them. The more space that is created, the less dense the air becomes. When the air is less dense, it rises. As this air rises, the denser and cooler air sinks. This is a circular motion that keeps the less dense air rising and the denser air sinking. As a result, the air closer to the heating source becomes less dense, and the more it cools, the denser it becomes. The steam is water that has heated so much that it changes from a liquid to a vapor. You can see on the boiling pot that the steam is rising away from the heat source. As the steam gets away from the stove, it cools down and condenses back to a liquid state. Now that you have a better understanding of convection, we'll talk about how it applies to insulation. Insulation mechanics deal with two types of convection. One is called natural convection. Natural convection is when the circulation of air is solar powered. The sun heats the air. When the air is heated, it rises. Then it cools and sinks. The other type of convection that mechanics deal with is called forced convection. This is where the air is circulated by mechanical means. This is oftentimes moved by a pump or a blower. The second method of heat transfer is conduction. Conduction is the heat transfer that happens within one solid or between two touching solids. Some materials are very good conductors. Metal is a good conductor. An example of this is when a pan has been on the stove and heated up. The pan is now hot, and so is the handle. If you were to touch the hot handle, your hand would then become hot. A material that does not conduct heat very well is plastic. Using our same example, you can use a plastic spoon to stir the pot while cooking without worrying about the spoon burning your hand. Now, let's talk about how this applies to insulation. Some insulation conducts heat more than others. In high temperature application, we might use a material like calcium silicate. It does a good job of holding the heat and not letting the heat convect through the material, but it does conduct heat. So, calcium silicate might feel hotter to touch than a fibrous material that is actually letting the heat convect or dissipate through the insulation. The third method of heat transfer is radiation. Heat is transferred through electromagnetic waves of a certain length known as radiation. The frequency of these waves is too low for us to see, but they are strong enough that you can feel the radiant heat. You know these properties exist when you aren't touching the stove, but you can feel the warmth by being near it. Just like with the conduction method, some materials are better radiators than others. A good radiator example is a blacktop road. As the sun shines upon it all day, it collects the heat, and as the sun sets and the air cools around it, the blacktop can still feel warm. An example of poor radiation material is aluminum. Many thermos containers have aluminum around the outside. This is because it keeps the heat inside because the aluminum material doesn't have radiation properties to allow heat to leave or enter the container. Using an infrared camera is a great way to see materials that have good radiation properties, materials that have poor radiation properties, and where there is a difference. Now that we know what the three types of heat transfer are, let's talk about 5 main reasons to insulate. All of these reasons center on the fact that mechanical insulation is affected by the ambient temperature that is directly surrounding the mechanical system. The first reason to insulate is to prevent heat transfer or loss of energy. Heat and energy is lost when there is a temperature difference between two objects. The transfer of heat always goes from a warmer item to a colder item. It can be between a solid and a solid, between a liquid and a solid, or between a liquid and a liquid. When insulating a heating system, we are stopping the escape of heat. When insulating a cold system, we are stopping the warmer outside temperature from reaching the cold system. The second reason to insulate is to conserve energy. As we discussed, insulation can go on either heating systems or on cooling systems. Both ways, it took energy to get the contents to the desired high or low temperature. Since proper insulation keeps the contents unaffected by the outside factors and maintains the inside status, we are conserving energy by reducing the amount of loss in those systems. We are also conserving the energy it took to create the heat or cold in those systems. Safety is the next major reason to insulate. Because the insulation around heating systems protects the hot liquid inside, it is also protecting the people on the outside. Burn protection is a major safety concern and an important reason to insulate when hot systems are going to be around people and important surroundings. Another aspect of safety is to control fire hazards. Not all materials are suited for insulation applications and could aid in spreading fire. With the knowledge of material and heat transfer properties, we are able to apply insulation with proper materials so the insulation doesn't add to the fire hazard. Not only are we working with fire-safe materials, many of our insulators are working on projects that go the extra fire safety step to apply fire stopping. Fire stopping is a measure insulators take when using compartmentalization to contain fire in the place of origin and stop the fire or smoke from spreading to other areas. Another main reason for insulating is to stop something from freezing. While it's important to maintain the ideal temperature of the contents in a heating or cooling system, it is important to not let the temperature become an extreme. If we were insulating a pipe that was carrying water and the temperature got below 32 degrees, the water would freeze. Water has the properties of many other materials and expands when it freezes. When the contents expand, the pipes are stretched. This could result in pipes bursting because of the material expansion. The final major reason to insulate is to prevent condensation. Condensation is formed when the ambient temperature is higher than what the temperature is inside the container. Closed-cell materials prevent outside air from reaching inside the container. An example of condensation being prevented is when you have a cold soda and you put a koozie on it. In our industry, the proper insulation can prevent a safety hazard by stopping condensation from dripping on a facility's floor or electrical system. Now that we know what heat transfer is and some of the major reasons to insulate, we're going to discuss some of the terms you will hear in the field. We want you to be familiar with these terms and how they are applied to the insulation you are installing. What is density? Density is the weight of 1 cubic foot of material. Very dense materials will allow heat transfer through conduction, but not through convection. Materials that are not dense will have low conduction properties, but high convection heat transfer rates. The best insulation materials have a good mixture of both convection and conduction properties. For most applications and depending on temperature, light and tight-celled materials work the most effective. A British thermal unit, also known as a BTU, is the amount of heat it takes to raise 1 gallon of water 1 degree Fahrenheit. Applying this unit of measurement to current terms, a calorie is the amount of heat it takes to raise 1 gram of water 1 degree Celsius. In the following examples, factor and value are the same. K factor is the amount of thermal conduction a material has the ability to insulate. The lower the K factor, the better the insulation. In most cases, the insulation materials we work with have a K factor of less than 1. To determine the K factor of materials, the manufacturer would measure the number of BTUs that would pass through a 1-inch thick material that is 1 foot long by 1 foot wide in 1 hour, with the two sides having a differing temperature of 1 degree. An ideal material will have a low K factor. Fiberglass has a K factor of 0.25, whereas calcium silicate material has a K factor of 0.38. C factor is the thermal conductance factor. Much like the K factor, it measures the rate of heat transfer through material. The C factor is dependent upon the thickness of the insulation. Thicker insulation material will have a lower C factor and will thus be a better material for insulation. To calculate the C factor, you divide the BTUs by the hour per square foot per degree of Fahrenheit temperature difference. The C factor can also be calculated if you know the K factor. Then it can be determined by dividing the K factor by the inches of thickness. The R factor is how much a material is resistant to conduction. There are several ways to determine the R factor. If you know the K factor of a material, you can use the following formula. R factor is equal to the thickness of the insulation divided by the K factor. An example would be for fiberglass that is 1.5 inches thick. We know fiberglass has a K factor of 0.25. Therefore, 1.5 inches divided by 0.25 equals an R factor of 6. If you know the C factor, the R factor can be calculated by taking 1 divided by the C factor. We hope this video has given you a basic understanding of the scientific principles behind mechanical insulation. Remember, you're an HFIAW professional whose craftsmanship and knowledge sets and continuously raises the industry standard.